today is jointly with João Vitor da Silva, Gleitson Riccardi, and Dernan Vivas. And this is I will talk about free boundary regularity for one-phase double degenerate fully nonlinear elliptic equations. João Vitor talked about double degenerate models this morning and explain a little about the problem that I will present to you today. And so I think he facilitated the understanding of my talk. And so to understand our problem, given a bounded domain, omega, okay, we investigate the double degenerate fully nonlinear elliptic equation of this type, okay, where this H has this growth condition, okay, for constants L1 and L2, positive and bounded, where this kappa behaves like this, okay? And the operator F is a uniformly elliptic operator, okay? The function Q is non-negative and continuous. The first term F is bounded and continuous. We will consider solutions U non-negative in omega. Okay, so we are dealing with a problem in one phase. And we consider the set omega plus about the points X where the solutions are positive. And the free boundary, which is formed by the boundary of this omega plus and the intersection with the omega. So in a first moment, we establish optimal Lipschitz regularity to viscosity solutions. And we also prove non-degeneracy of solutions. And then we will investigate the regularity of the free boundary, okay? And our first find is that flat free boundaries are of class C1 beta. And finally, we will prove that Lipschitz free boundaries are of class C1 beta. One of the main signature of this model in which we are investigating is that it's interplay between two different kinds of degeneracy laws, okay, according with this modulate function A. So this function A is non-negative and continuous, okay, and this P and Q are positive and bounded, where P is less than Q. And this model can be considered a non-divergence form of certain variational integrals from the calculus of variations, where in the double phase structure, where we are looking in the minimization problem of this functional, okay, where omega F is in the set. And in this case, A is of class C alpha for some alpha between 0 and 1. And P and Q is greater than 1 and bounded. M is between N and infinity. And this kind of, for problems like this, we can see the works of Baroni, Colombi, Mingioni in 2008, Colombi, Mingioni in 2050, De Philippis Mingioni in 2020, and De Philippis in 2009. So historically, the mathematical investigation of the regularity of the free boundary in problems like we are investigating has a large literature. So in the uniform elliptic case, for the variational approach, when you have the first term is 0 and the H equals 1, We have the works of Caffarelli in 1981, and the works of Caffarelli in 87 and 89, where they studied the functional, this kind of functional. So they minimizing this function, and they prove the existence of a minimal, and also the regularity of the free boundary via blow up techniques or via singular perturbation methods for the problem like this. Okay. So in the degenerate case, still in the variational approach, we may first quote the work of Daniele Petrosian in 2005, in which they established the regularity near flat points of the free boundary of non-negative solution to this minimization problem. Okay. So this functional is governed by the P-Laplacian operator. And we also have, in the Orlik-Sobolev scenario, we have the work of Martinez and Volansky in 2008, where they studied the minimizing, the problem of minimizing this functional. And for the study of existing Lipschitz regularity and regularity of the free boundary for homogeneous and inhomogeneous free boundary problems, driven by the PDX Laplacian type operators like this problem, okay, can be found in the works of Fernandes Bonder, Martinez and Volansky in 2010, and the works of Lederman and Volansky in 2017, 2019, and 2021. In the non-variation approach, when the constant is the fully nonlinear elliptic equations, when the source term is 0 and h is 1, we have the work of Feldman in 2001 and the references therein. And on the other hand, for the non-homogeneous case, this means that f is different by 0. This was studied in the series of the Silva and the et al.'s fundamental works, like in this work in the Silva, the interfaces and free boundaries is 2011, and the Silva Ferrari Salsa in 2015, both in the one and two phase scenarios. Okay. So in turn, the free boundary considered in one also appears as the limit of certain homogeneous singularly perturbed problems in the non-variation constants of high energy activation model in combustion and flame propagation theories, as we can see in the works of Araújo, Ricardo and Teixeira in 2017, Ricardo and Silva in 2015, and Ricardo Teixeira in 2011. And the simplest mathematical model in this case is given by, for each epsilon fixed, we seek a non-negative profile U epsilon satisfy this problem, okay? In the viscosity sense, for suitable data P and Q, A and G, where this beta epsilon behaves singular of order 1 over epsilon near epsilon level surface, okay? And in this scenario, existing solutions are locally uniformly Lipschitz continuous, as we can see in the work of Da Silva, Junior, Ricardo to appear. So, to understand our problem, first I will remember the definition of viscosity solution. So if we have a continuous function non-negative, we say that U is a viscosity subsolution or subsolution to this problem, if and only if the following conditions are satisfied. So if you have phi in C2 touching by you by balance, okay, or above, at x0 in the omega plus, then this inequality needs to happen, okay? And if x0 is in the free boundary and the gradient of phi is different of 0, then this the gradient of phi in x0 needs to be less or equal to q x0. And we say that you use a viscous solution if it's a viscous super solution and a viscous sub-solution. In our work, we are supposing that F is a continuous in the set of symmetric matrices. And in the matrix, in the zero matrix, we are supposing that F is 0, okay? And by uniform ellipticity, we mean that for any pair of matrices X and Y in the set of symmetric matrices, this condition happens, okay? Where these two operators are the put extreme operators defined by this, okay? For ellipticity constants lambda and capital lambda positive and bounded. And the EI are the eigenvalues of X. So we also suppose that there exists a uniform modulus of continued omega and a constant CF such that this supremum is bounded by CF, the modulus of continuum in X minus X0. And this measures the oscillation of the coefficients of F around X0. So, and we also define this norm, okay, that I will mention later. In our studies, the diffusion properties of the model degenerate along an a priori unknown set of singular points, which means that the points where the gradient of U is 0. And for this reason, we will enforce that the H behaves like this, okay, for L1 and L2 positive and bounded, and the kappa behaves like this. In addition, we are supposing that the exponents P and Q are positive. P is less than or equal to Q and is bounded. And the function A is continuous. And finally, we assume that there exists a universal constant CA and a modulus of continuous omega A such that this condition happens. Okay. So our first result is the optimal Lipschitz regularity. This means that for Q in continuous and bounded, and U a bounded viscous solution, there exists a universal constant C1 such that U is bounded by this condition, okay? This means that solutions have at most linear behavior close to the free boundary points. And in particular, there exists C2 such that the gradient of U is bounded by this, okay? And the proof of the Lipschitz regularity, for the proof of Lipschitz regularity, we employ the ideas of the works of Araújo, Ricarte, and Teixeira, da Silva, Júnior, and Ricarte, and Ricarte Silva, and Ricarte Silva, Temurazian, and Ricarte Teixeira, performed for the scenario of singularly perturbated free boundary problems. And the idea is the general idea, okay, is to take a x0 in behalf such that x0 is in behalf plus, okay? And also we suppose that the distance of x0 until the free boundary is less than or equal to half. And we consider this scaled function. And the general idea is to prove that this v in 0 is bounded by a constant c0. So here we use, we construct some barrier, we use the comparison principle, use the Harnack inequality, and the C1 beta integral estimates that already have proved by Cristiano De Filippis in 2020. And then we have the non-degeneracy of solutions. That means that here we suppose that the free boundary is the Lipschitz graph in B1, okay? And the free boundary intersection with B half plus is different of empty. So there exists a universal neta 0 and a universal constant C star, such that if Q is close to 1 by neta 0, then U is greater than or equal to C star distance of x0 to the free boundary. This is for all x0 in behalf plus. This means that solutions grow at least in a linear fashion close to the free boundary points. So for the proof of the non-degeneracy result, we argue, as in the work of Daniela de Silva in 2011, after constructing the appropriate barrier. And then we use like the same idea of the proof of the Lipschitz continuum, but here we need to prove that V in 0 is greater than or equal to C star. And here we use the Harnack inequality and the Lipschitz continuum already proved. And for the free boundary regularity, we have two main results. The first one is that flatness free boundaries implies that free boundaries are of class C1 beta. Here, we suppose that 0 is in the free boundary, Q ends in 0 is equal 1, and F is uniformly elliptic. So there exists a universal constant epsilon tilde, such that if the graph of U is epsilon tilde flat in B1, this means that this happens, okay? And the maximum of these three norms are small, okay, by epsilon tilde. Then the free boundary is of class C1 beta in behalf for some universal beta in 0, between 0 and 1. So the proof of this theorem is based on an improvement of flatness, which comes from the Harnack type inequality and Harnack type estimates, okay? And follow the ideas of Daniela de Silva in 2011. So the main idea is to integrate the following lemma in appropriate geometric scaling. The lemma consists in under smaller assumptions of the source term and the Q minus 1 with 0. With 0 in the free boundary, if you assume that this happens, okay, then there exists universal constants R0 such that if R is small and epsilon is less than or equal to epsilon 0, where this epsilon 0 depends on the radius of the ball, then this happens, okay, where this Ni is in the unity sphere, okay, and Ni minus the vector En is less than or equal to C epsilon square. The main difficulty of this theorem is to prove that this lemma, okay? And the main ingredient to prove this lemma is a Harnack inequality. So the main difficulty that we need to overcome is in the Harnack inequality, okay? In fact, if L is an affine function and U is a solution to the problem that we are working, we cannot conclude that U plus L is a solution to this equation. So this is in contrast of in the case where P is equal, Q is equal 0, where we know that U plus L is still a solution for 2, where the Daniela de Silva have used this fact which allow us to apply the Harnack inequality for this function, okay? And this function plays a crucial role in reaching the previous lemma that is the improvement of flatness for the graph of U. So this theorem is very technical, and the main difficulty that you need to overcome is to prove the Harnack inequality. And the last result is that Lipschitz free boundary implies C1 beta. And this means that if 0 is in the free boundary, F is a bounded function and continuous, and Q in 0 is positive. If the free boundary is a Lipschitz graph in the neighborhood of 0, then the free boundary of U is C1 beta in a smaller neighborhood of 0, okay? And to prove this, we use a blow-up argument from the previous theorem, and we use the approach used in the work of Caffarelli in 1987, okay? And the main idea is consider we scale the functions like this, okay, where delta k goes to 0 as k goes to infinity. And because of the non-degeneracy and the Lipschitz continuity for UKs, we have the UK goes to function U infinity uniformly on compact sets, okay? And then we can prove that the limit profile U infinity solves this problem, okay? With the free boundary for U infinity is Lipschitz continuous, and we prove this via compactness lemma and using a Canting lemma. And we also can prove that U infinity is a one-phase solution. So this means that up to rotations, U infinity is equal to xn plus. And then for k large enough, we have that UK is close to U infinity by epsilon tilde, where this epsilon tilde comes from the previous theorem. And so UK fulfills epsilon flat in B1, and then it implies that the free boundary for UK is a graph C1 beta for the previous theorem, and consequently we have that the free boundary are of class C1 beta for some beta between 0 and 1. So I think I stop here, and thank you for the attention.